Well, as Emily just introduced, my name is Feria Lozel, and I'm an astrophysicist. I'm a professor at Georgia Tech and a general member of the Aspen Center for Physics for 8 years. I would like to extend a warm welcome to all of you to tonight's public lecture, sponsored by the Nick and Maggie DeWolf Foundation, which has supported these public lectures in Aspen since 1985, which makes it this the 40th year that these lectures are going on. Their generosity and the generosity of every lecturer, like the one we have tonight, makes it possible to share the new research that is the frontier of science forward. It's our way of thanking the Aspen community for supporting the center. During the winter, like we are right now, groups of up to 110 physicists come here, gather at the Aspen Center for Physics, and spend an intensive week sharing the latest research with their colleagues in formal meetings, also informally on the slopes and, on the trails, on the cross-country trails. We are here this week participating in the Era of Binary Supermassive Black Holes conference. We're discussing how we find and study not just individual black holes at the centers of galaxies, but pairs of black holes at the centers of galaxies through gravitational waves and all wavelengths of light. We are discussing how these pairs come together and merge in the cosmic evolution and how they affect the galaxies that host them. So this has been the past few days for us, which has been exciting. Our discussions have been lively, and that is no surprise. Aspen is a great place for inspiration, winter and summer. For me, it provides the perfect blend of quiet and excitement and uninterrupted time discussing new ideas with great colleagues who gather here. Despite long days, we leave refreshed with new ideas and too many projects to work on. I'm delighted to be a part of this community, and I'm grateful for our ties with all of you, the community in Aspen. Tonight, we have the pleasure of having Dr. Jillian Bellaveri as our speaker. Dr. Bellaveri is a faculty in physics at CUNY, Queensborough Community College, and a research associate at the American Museum of Natural History in New York City. She received her PhD in astronomy in 2010 at the University of Washington, working on the formation and evolution of massive black holes. She's an expert on the subject and has been a member of the study team for LISA, which is an upcoming space mission designed to detect gravitational waves from coalescing black holes. Dr. Bellaveri is also a leader and a dedicated contributor to bridge programs, which give students from many backgrounds access to graduate school in astronomy and physics, increasing the reach of physics and astronomy. So without further ado, this evening, Dr. Bellaveri will tell us about unraveling the cosmic melody of black holes. Please join me in welcoming her.
Okay, wonderful. Thank you so much for having me here. My first time at the Aspen Center of Physics was in 2010 when I was just about to graduate as a PhD student. So it was a memorable time, and it's great to be back here doing this. So before I begin, and before I share my wonderful love for black holes with all of you, I have a task for us. So you have an assignment. I'm going to move out of the recording camera part for a second. I'm sorry, but I have to do this. All right. We're going to divide the room in half. And so this is the halfway point. You're either on this half, or this half. If I am bisecting you, you can decide which half you would like to be on. That doesn't actually matter that much. Okay. So the activity that we are going to do is that when I give the word, half of the room, we'll denote which half, is just going to close their eyes and listen. And the other half of the room would like you to talk. You can talk to the person next to you. If you don't know the person next to you, feel free to introduce yourself. Talk about where you live and what you do and whatever you would like to say, what your favorite color is. If you want, you can speak loudly or speak quietly. You can sing if you like. that would be fine too. Make noise with your voice for a little while. And then I'm going to switch and have the other side of the room do the quiet listening with your eyes closed, and the other side do the talking. Any questions about your assignment? Got it. Okay. So for the first half, we'll have this side of the room talk, and this side of the room close your eyes and listen to the voices. Ready? Go. Okay. Thank you very much. That was perfect. You did great. Now we're going to switch. So with this side of the room, please talk, and this side, close your eyes and listen. Go for it.
What's your favorite color?
All right. Excellent. Great job, everybody. Hope you made a new friend. But while you were listening, think about silencing your phone if you haven't done so already, and then think about what you heard. Did you hear? Could you like what did you hear? Anybody?
Cacophony of noise.
A cacophony of noise. They were talking. Okay, so they're talking about you. Okay, yeah.
I tried to concentrate when I was listening, and I couldn't tell that only that side was talking and this side wasn't. It seemed like everybody was talking all around me.
Okay, so it seemed like it kind of came from everywhere. Probably the acoustics in this room probably help with that. Until it's been engineered in a cool way. Anybody hear individual voices, like individual words? A little bit, yeah. And most of the people who are saying yes are kind of on the border. So you were probably right next to somebody who was talking. People on the edges, you just heard more of kind of a fuzzy sound. Okay. So this is going to be part of our analogy for black holes tonight. Stick with me here. So if you have a crowd of people like we have here, and if you wanted to figure out who's in the crowd, you could count the people in this picture. That would take a while, but you could do it. If you wanted to figure out like specifics, like how many people are wearing red shirts, or how many people are wearing hats, or how many people look young or old, based on whatever criteria you want, you could do that. But we can also hear the crowd. And what I had you do just now is I had you close your eyes and just use your ears. And so how can we learn about the crowd if we can't see it? We don't have any eyes and just ears. How can we learn about things like who is in the crowd, what people are there, how big is the crowd, how many people are there, and if you want to get real particular, what are people actually saying, which most of you in this experiment couldn't figure out unless you were right next to somebody who was talking. Then you could tell that they were talking about what you were doing, like knitting at that particular moment. Okay. And so this crowd noise is going to be our analogy for emerging black holes. So hang on with me here. So our analogy, a person in a crowd who is talking is going to equal a pair of merging supermassive black holes. Right? And this analogy is going to carry us through the evening, the next 40 or so minutes of your life. So just keep this in mind, and I'll keep referring back to it. All right? Okay. So first, let's start from the basics. What is a supermassive black hole? It's a big black circle with a question mark. We really don't know a lot of things about them, but things we do know are they have really strong gravity, so strong that light cannot escape. And so that means that if you were, say, inside of a black hole and shone a flashlight up toward the sky, that beam of light would then curve and fall back down towards you. just like something that you throw up in the air, falls back towards you. So would light, because it cannot escape the black hole. That's so weird. Isn't that weird? That's weird. All right. Supermassive black holes are a particular genre of black hole that are between 1,000,000 and 1,000,000,000 times the mass of the sun. Supermassive is a very appropriate word. They are giant. They can also be bright, which you might say, didn't she just say that light could not escape? How can they be bright? She's already messing it up. But no, just wait. Here is a picture of a supermassive black hole in the nearby galaxy M87. And the black hole itself is the dark circle in the center. And the glowing donut around it is actually gas that is falling into or accreting onto the black hole. And so the black holes themselves do not emit light. But if you've got gas that's right next to a black hole, as it's falling into a black hole, it will actually glow. So my little cartoon version of that. So your gas clouds fall in, they emit a bunch of light as they do that. And some of the brightest objects in the universe are called quasars. And that is exactly what is going on in a quasar. You have a supermassive black hole. You have gas that is falling into it. And that gas, as it speeds up and spins around, glows very, very brightly and makes the brightest things that we have in the universe. If you've ever heard of a quasar, it is a supermassive black hole that is really eating lunch, basically, having some gas for lunch, right? So supermassive black holes are awesome, but there's also a lot that we don't know about them. They're so cool because they're so powerful, but we don't know how they form. How do you make a supermassive black hole? We don't know. We do know that supermassive black holes have been around a really long time. And we use powerful telescopes like Hubble Space Telescope or the James Webb Space Telescope and look at the most distant galaxies, which are galaxies from the earliest parts of the universe. There are supermassive black holes then, which means just a little bit after the universe formed from the Big Bang, somehow 1 billion suns worth of stuff got crammed into a space the size of our solar system really fast. How? We have no idea. I mean, we have a lot of ideas, but they're probably all wrong. We don't really know. This is a big mystery. And so this is why solving them or studying them is really interesting to solve these. We don't understand how they affect their surroundings either. So I talked about that quasar, and you've got a bunch of light coming out. That can affect the whole environment that the black hole is in, even like really, really far away from the black hole. Like, how does this black hole over here affect something way over there? We're not really sure. We also don't know how or if they merge with each other. Einstein said they did over 100 years ago. He's like, oh, black holes will merge and they'll make gravitational waves. And everyone's like, oh, cool, that sounds nice. But now we know about that. And we know that some black holes merge and make gravitational waves. I'll talk about that in a minute. But supermassive black holes, we've never actually seen it happen. We haven't seen them merge. We think they do, because we've seen other black holes merge, and when we look in the centers of galaxies, we think we see just one black hole and not 2, 7, or however many there might be. So they probably do, but we don't understand how that works. But that is why we are here. We want to understand how that works. So, there's all the things that we don't know. What do we know? We know where black holes live. Supermassive black holes live in galaxies. Here are some beautiful galaxies. We have a spiral galaxy on the left, an elliptical galaxy on the right. The spiral has spiral arms, and the elliptical is kind of a cosmic potato shape, but they're nice too. Galaxies are made of stars. They're made of gas. They're made of dust. You can see the dust in the spiral galaxy. There's some sort of dark. Can I use this? Nope, I'm going to break everything. You still hear me? Am I still on? Okay, good. Cool. There's some dark lines here and here. That's dust. There's also dark matter in galaxies. You cannot see that. It is invisible. But, of course, there are also supermassive black holes in the centers of massive galaxies. We know that they're there. And when we watch and see what galaxies are doing, we are pretty sure that galaxies do interact with each other. Let me get this movie to play. Cue YouTube. All right. What I'm going to show you is a simulation. This movie is so it's not real. It's not actual galaxies, but it's what we think would happen if we took our Milky Way galaxy and our nearby neighbor Andromeda galaxy and smashed them into each other, which will happen 3 billion years from now, which is not soon. So you should still plan your ski trips and things like that. So we've got our two galaxies, and what we're going to do is put them on a sort of collision course toward each other in a way that we think would really happen. And remember, in reality, not the simulation, these galaxies would have supermassive black holes in their center. You just can't see them here. Here we go. Oh, isn't that cool? Yeah. Guess what? It's going to happen again. So it makes a mess. And then eventually they coalesce, form a single galaxy. So this is something that we can simulate happening. And when we look at galaxies in the universe, we see stuff like this. And clearly, these are galaxies doing what we just saw in that movie. These galaxies are in the process of smashing together, making a big mess. Eventually, in a billion or so years, they will just be one galaxy with maybe some wispy stuff around it, but it'll probably look kind of like that elliptical galaxy I showed you earlier. So these merging galaxies have supermassive black holes in them. And so what we think will happen is that since our galaxies merge, supermassive black holes should probably merge too. I'm going to teach you some basic math. It's a little different from your arithmetic that you learned in school. Instead of the normal 1 + 1 = 2, when we have galaxy plus galaxy, you get a bigger galaxy. So 1 + 1 = a bigger one. And when you add those black holes together, you have 1 + 1 = first of all, they'll probably be a little bit apart, but then they'll kind of orbit and merge together and then make a bigger black hole as well. This is what we think happens in my cartoon style, right? So there's some basics on supermassive black holes. And I want to remember our analogy now. We're going to go back, check in on this. Remember that a person in a crowd who you may have been overhearing a moment ago is, in our analogy, equivalent to merging supermassive black holes. So now I've explained supermassive black holes, explained that they merge, but how is a person in a crowd talking like this? You might ask, what's the noise? Do black holes make noise? No, there's no noise in space. No one can hear you scream, right? Oh, no one can hear black holes either. There isn't noise, but there is something that's kind of analogous to noise, and that is gravitational waves. What the heck? Gravitational waves. They sound really cool, don't they? But what are they? Gravitational waves are ripples in space-time. Was that helpful? No? Maybe? What is space-time? Okay, so what the heck is all this? So, remember, supermassive black holes, merging, gravitational waves, what are they? What is space-time? Space-time is the underlying fabric of the universe, and it bends when there are things with mass around. If you imagine I were to hold a bed sheet out in front of us and we would pull it tight, if I put a golf ball and tossed it onto the bed sheet, it would make a little dent. And if I put a baseball onto the bed sheet, it would make a bigger dent. And if I put a bowling ball onto the bed sheet, it would probably hit the floor, unless we're holding the sheet tight enough. So it'd make a really big dent. Heavier thing, deeper dent in the sheet. Space-time is kind of like this. The more mass you have, the more space and time bend around that mass. So I wonder if, can you see my little, oh, you can, okay. You can see my arrow. So you can see that if you've got the sun on our sheet of space-time, and if you're going on a path that's going nearby the sun, you would go, oh, I'm getting toward the sun. Then you might follow this line and go away from the sun. But you would bend, space is bending toward it. So a path of a beam of light or a satellite or a spaceship would bend along that curved space-time. Things with more mass bend it more. So I've got this thing here called a neutron star. We're going to come back to these later. Neutron stars are the dead cores of really big exploded stars. So they're kind of like this leftover corpse, if you will, but it's still really awesome and great. And so they're bigger, they're more massive than the sun, and so they bend space-time even more. But black holes are the awesomest things in the universe, and they bend space-time the most. And supermassive black holes definitely really bend it a lot. So here's a cartoon picture of black holes, which are weirdly shiny for some reason. That's not right. But black holes bending space-time by sitting in your bed sheet and curving the space around them. So there's our binary black hole system. Okay, so they warp space, and that's really cool. How do you make gravitational waves? So if we're going to make gravitational waves, our recipe is we need some dense, massive things. 2 of them is pretty good. We're going to bring them close together. We're going to shake them up a little bit, maybe have them orbit each other, stir them around, and eventually smash them together. And that effect on the surrounding space-time causes ripples in it, causing gravitational waves. All right, I've got a couple of animations to help get this point across, because I know even though I can see some of you nodding, but this is still like super weird. This is weird stuff. So I'm gonna work on, we're gonna go over it a couple times. So here is an animation of 2 black holes that are merging, and the colors are the warped space-time. Okay? And so you can see the below these 2 black holes that are in an orbit, there's like these rainbow pits, and that's the warped space-time. And so as the black holes get closer together, you can start to see that these pits are getting closer as well. Eventually, they start to kind of overlap. The black holes are turning red. I don't know what that quite means. But the black holes' orbits are speeding up. And then the movie gets real slow because space-time gets super strange right here. Like space and time are all bending in this strange way. And then the movie freezes and the black holes coalesce. And then there's one black hole. And it all just sort of like goes back to normal. Oh, and there we are. With our gravitational waves flowing outwards. That is a pretty cool movie showing some of that. There's some cool credits. Thank you to these people who made this movie. All right. So ripples in space-time are kind of like water droplets in a puddle, where you have your black hole binary and then merging, and then there's sort of a splash, and then they spread outwards. But they don't actually spread outwards in 2 dimensions like a puddle. They spread outwards in 3 dimensions because we have 3 space dimensions. But it is very hard to think about this happening in 3 dimensions, so a puddle is a pretty good analogy. Okay. This is a movie showing the 3 dimensions of how gravitational wave radiation propagates outward. So we have, again, 2 merging black holes, and you can see the sort of warped space-time around them, and the shape of the gravitational wave emission is really, really odd. And then the black holes merge. And then you just got your one guy sitting there. And watch it again. This is really cool. Yeah. This is really cool. Thank you, NASA, for making an awesome movie. Yeah, so the actual 3-dimensional shape of the gravitational waves is pretty complicated. Really cool looking. Isn't that cool? Yeah. Yes, that is so cool. All right, cool. All right, let's go on then. So, what do gravitational waves do? What they do to space is actually stretch and squeeze it. And so they alternately, as they go through, say, it's a cartoon person, stretch the person, and then squish the person. Where should I put my yardstick? I have an example here. Fariel, would you help me demo something? All you have to do is stand here.
Wait, make me. Yes.
Would you stand by the purple line? Okay.
Then.
Safe. No gravitational waves will harm you in this experiment. Okay. Fariel and I are 1 yard apart. This is a yardstick, not a meter stick. It's specifically a yardstick. Okay. if a gravitational wave were to propagate through us in such a way that it was so strong that we would notice it, we would, from your point of view, it would look like we would kind of do this to each other, like go back and forth. What's actually happening is that this distance of 1 yard is actually changing, that it's getting, 1 yard is getting shorter, and then 1 yard is getting longer, shorter and longer. And so even as we are like doing this kind of thing, we are always 1 yard apart. Space itself stretching and squishing. So what a yard is changing. Yes. Thank you. So that's super strange and very weird. I have a movie here of a super exaggerated what would happen if a bunch of gravitational waves went through the Earth. These green whooshes are gravitational waves, and you can see the Earth like squishing and stretching, it's squishing and stretching, and then wobbling. It's so strange. It's vastly exaggerated. Gravitational waves are going through our bodies now, but they're shifting us like the protons in the atoms in our body are shifting like by 1,000th of their position. Like, it's so not noticeable. Promise you do not notice gravitational waves. Way more annoying things to notice than gravitational waves. They're super hard to measure. We have detected them. Oh, you may have heard of something called LIGO or LIGO Virgo or LIGO Virgo Kagra, which is now a long name. This is a picture of the LIGO instrument in Hanford, Washington. Each of these arms are 2.5 miles long. And this instrument, along with its partner instruments, has detected gravitational waves from merging black holes. But they are smaller than supermassive black holes. What this cool raven-shaped plot shows is the vertical axis here is the mass, and so these are the most massive black holes, and then these are like smaller black holes. And so it shows, for example, one black hole and another black hole merging together to make a final black hole. And so that's what all these vertical lines are. So, so those are all of the black holes mergers that LIGO has seen. Some neutron star mergers are down here in orange. And then black holes that are known from light instead of from gravitational waves are in the red on the sides. Neutron stars that we know about from light, these yellow things. Something that's cool here is that we know about more black holes from gravitational wave mergers than we do from using telescopes. Hey, that is cool. This has only been going for like 10 years. That is cool. Gravitational waves are super powerful. And another thing that is really cool is that we can learn about them without any light. None of these black hole mergers have any light associated with them. Two black holes merging together without any gas in their environment, it's dark. There's nothing to see. You could look at it with your telescope, you won't see anything. Sad, but true. And so think about in a world where we don't know about gravitational waves, we wouldn't know about any of those black hole mergers. We would know very much about black hole mergers at all. It's like we have a whole nother sense to discover things about the universe besides using telescopes and using our eyes. That is awesome. That is so awesome. Gravitational waves, great. And I love them. Hope you love them too. So LIGO is really great, detecting gravitational waves, possibly as we speak. A future mission that I am affiliated with is called LISA, which is going to be kind of like LIGO, but way bigger and in space. What could be better than LIGO? Space LIGO, but bigger. It's going to be enormous. It's going to actually follow the Earth in its orbit. So if you look at this little picture in this corner, there's a little blue dot that's a little hard to see, but it's orbiting. And then this triangle is the LISA instrument with lasers connecting these different little satellites, and it's going to follow the Earth in its orbit. The size of this instrument, the distance between one part to another, is more than 5 times the Earth-Moon distance. So what this is going to do is it's going to detect mergers from things like intermediate mass black holes, which are bigger than the stellar black holes that LIGO discovers, but smaller than supermassive black holes. So for this to work, we needed to make a detector that's kind of on the scale of the size of the solar system. That's big. And so to detect even bigger black holes, you would need even a bigger detector, and we just can't really build anything that's bigger than any place we've ever sent any type of thing. So it's just not on the docket right now. So this mission, which is a partnership between NASA and the European Space Agency, will launch in the mid-2030s and discover even more black hole mergers or medium-sized black holes and a whole bunch of other things too, which I don't have time to talk about now, but I also like those things. They're just not merging black holes. Everything's cool though. Okay, so we've talked about merging smaller black holes and medium black holes, but supermassive black holes haven't yet built anything to detect their mergers, and that's partly because their mergers happen more slowly. They actually orbit for a long time. They orbit for a long time before they merge together, and that during that orbit they'll be emitting gravitational waves, but it can go on for a long, long time. And the actual merger isn't going to be quite common, we don't think. Something that we can see with LISA or with LIGO. So if we have a whole bunch of mergers going on at once, a whole bunch of black holes that are orbiting each other, like my conga line here, orbiting each other at once, instead of one single drop in a puddle, we kind of see is a whole puddle, a whole pond with raindrops. And so if we're like, well, there's a bunch of black holes that are orbiting and going to merge, but like some are here and some are there, and then they're overlapping, and that splash is bigger and that splash is smaller, and how do we figure all this out? It's actually pretty hard, because if we want to measure gravitational waves from merging black holes all around us in the universe, and a lot of them are going to be emitting gravitational waves, but how are we going to figure out what the signal is and tell them apart from each other? It's difficult. So, that'll bring us back to our analogy. Remember, a person talking is like a merging supermassive black hole. If we have many voices talking at once, if a whole crowd of supermassive black holes, how do we hear noise? How are we going to detect these gravitational waves? I'm going to ask you this. If you were going to try and hear a crowd, and you wanted to do a better job of it and learn more about who was in the crowd, what would you do? Anybody have any ideas?
Close.
Okay, get closer is a good idea, but you can't get closer. You're stuck in your seat. What else would you do? You can't move the earth.
Aim a hearing device close to one individual.
Aha, a hearing device. Yes, we could use hearing devices. What do we call those? Microphones. Aha. So if we wanted to hear a crowd, we wanted to do a better job of hearing the crowd, we could use microphones. We could use more microphones. We could get really good, awesome, better microphones. We could make an array of microphones like all over this room. And then if we set up the microphones right, we could actually maybe hear what each person was saying. And so we would make an array of microphones. So what we need in space is an array of microphones to hear gravitational waves. What is our microphone? Turns out that our microphone is going to be this thing called pulsar. Here's a cartoon of a pulsar. What is a pulsar? A pulsar is a type of neutron star. I mentioned those earlier. They're dense head cores of massive stars. They're so dense. So if you had a teaspoon of a neutron star, it would weigh 4 billion tons. Which for me as a New Yorker, I compare to the Empire State Building because we always do that. It's 10,000 Empire State Buildings in a teaspoon. I was trying to find a better analogy, like could it be Aspen Mountain in a teaspoon, but I couldn't figure out how much Aspen Mountain weighed, and so I didn't get that. But so they're very dense, they're very weird. They're maybe even as weird as black holes. I don't know. They're weird, they're differently weird. They're great, they're totally great. They spin really fast. So that's one of their main properties of pulsars is that they spin. Sometimes they'll spin like once per second, and sometimes they'll spin even faster, like 1,000 times per second. So spinning really, really quickly. They also emit these beams of light out of their magnetic poles. You can see there's sort of a top beam and a bottom beam. You can kind of imagine a magnet here, like a north pole of a magnet, the south pole of a magnet, and due to some really funky physics going on in our neutron star, we've got beams of light going out of these magnets. That turns out to be important because, get this movie to play. It wouldn't play earlier. And then it did. Let's see, can we play a movie? Yes, okay. So, sometimes as this pulsar is spinning, a beam of light flashes right at us, kind of like a lighthouse. Okay. So this happens at a pretty regular interval, and on the bottom of this movie here, you can see how there's a little peak every time the pulse or the light beam flashes at us. Okay? And so pulsars are really, really handy because they make these pulses at really regular intervals. And they were first discovered by Jocelyn Bell Burnell a long time ago. She actually thought they might be aliens, because who else would flash lights at us at regular intervals? But turns out it's actually just a cosmic object that is doing that and not aliens. And so this is really handy because since these things come at regular intervals, you can use them as a microphone, and I will show you how. Okay, so remember, checking in again, orbiting black holes generate gravitational waves. Gravitational waves stretch and squeeze space-time, and curving space-time will change the path of light. If you've got a pulsar here, and you've got Earth over here, but space-time is squished and squeezed, then the path of the light is going to change, which means that the cadence with which we get the pulses of light is also going to change. I have a animation here to show you. Here's an example. I'm going to pause it right there of a pulsar making pulses of light that go to Earth, and that's what we detect. But if it turns out there's actually a gravitational wave passing through space at that time, actual pulses that we see flashing in that happen are flashing in green there. What we have to do is use a model and match them. So because the pulses that we receive from the pulsar are different from what we expect based on what the pulsar is doing, that difference happens because space has been stretched and squeezed in between the pulsar and us. And we can do some calculations and figure out and rematch the pulsar pulses and then calculate the effect of the gravitational wave. That is how we can use this pulsar as kind of a microphone, because it can measure the stretching of space in between us and it from gravitational waves. But there isn't just one pulsar. Remember how I talked about an array of microphones? There are pulsars all around the Milky Way galaxy. You have an array of pulsars that are basically an array of gravitational wave microphones. You can see each pulsar might have a different shaped pulse. It's a different distance away. It's acting a little differently. But if we take really good measurements of each pulsar and calculate what we expect from each one, we can figure out the effect of gravitational waves from all of these different pulsars. This is an animation. Is it going to move? Can do it. Try and go back. Or there we go. Showing a cartoon of our galaxy, but then a map of all of the pulsars we know about. There's a little "you are here" in the middle there. Okay? As you can see, they're spinning around. They kind of look like little propellers. And so those are the pulsars that we know about in our galaxy that we can use as this array of microphones. Okay? So there's 70-something of them, I do believe. There's a lot. It's pretty great. How do we make sense of this? How do we figure it out? I have a cartoon here to explain it. So let's say here's Earth, here's two pulsars, and here is a gravitational wave front that's going towards the Earth through these pulsars. So these pulsars, because they're near each other in the sky, like angular wise, this gravitational wave is going to affect the space-time and affect the pulses from these pulsars to Earth in kind of the same way. So we would say that the pulses from those pulsars are correlated because they're affected in the same way by this one gravitational wave going through, because they're in the same part of the sky. We move the pulsar a little bit, say, okay, well, it's at a little bit of an angle now, so it's still correlated, but maybe a little less, because now it's kind of at an angle, and so the pulses wouldn't be stretched and squeezed in exactly the same way as they would if they were lined up. Cool? All right. What about if we have that guy down there? Its pulses are going to be stretched and squeezed in a way that has nothing to do with the way with this one up on the top. Okay, because this gravitational wave is coming through it at a different angle. So the way that space is stretched and squeezed will affect this one completely differently. So because this one is perpendicular, we say that these are uncorrelated. So these pulses will have nothing to do with each other. This one, this one in the back on the other side of the Earth, it's because the gravitational wave is going at the same angle, just kind of the other way toward this pulsar, it will be still a little correlated with the pulses of this other pulsar because the angle here is kind of the same. It won't be as awesomely correlated as this one that was right next to it because it's on the other side, but it's still a little bit correlated. So when we have all of our pulsars in an array, we can measure the correlations between all of them, figure out what the gravitational waves are like. Okay, so I'm going to show you a graph here that will have stuff on it soon, but for now I'm going to explain the graph. So the vertical axis of this graph is the correlation strength. So at the top, if things are high up on the graph, the pulsar signals will be correlated, like I explained just before. At the bottom, there's negative numbers. The pulsar signals are not correlated. X-axis, if stuff is on the left side, that's nearby in the sky in an angular sense, so it's the pulsar sky separation in degrees. If something is on the right side, it means they're opposite each other in the sky. So 0 degrees, 90 degrees, 180 degrees. All right. I'm going to fill in this graph now. If there were no gravitational waves, all of the pulsars together would be uncorrelated. We would have a straight line at 0, no correlation, or no gravitational waves. With gravitational waves, the ones that are close together are correlated, the ones that are 90 degrees apart are not, and then once they're 180 degrees apart again, they are correlated again, but a little less than before. Okay? So on this graph of how much correlation versus angle in the sky, if there are gravitational waves from merging supermassive black holes or from anything else, we would expect this kind of curvy shape if we were to measure the correlation of the pulsars. That's what we would expect. I have one more little cartoon of it to show you. Here's our correlated pulsar signal, ones that are at the similar angle, right angle of pulsars uncorrelated, and then opposite from each other pulsars, kind of correlated. Right. So how do we even measure this? What do we do? There's this whole international organization called the International Pulsar Timing Array. All over the world, telescopes from pretty much every continent are looking at all of these pulsars as much as they can to check out when these pulses are arriving. Scientists are calculating what the signals are, what the pulsar is actually doing, what gravitational wave signal is left over. And people in this organization have been looking for 15 years. That's a long time. What were you doing 15 years ago? I was a PhD student at the Aspen Center for Physics hoping to graduate and get a job. That's what I was doing 15 years ago. But for 15 years, people have been looking, and a little over a year ago, they published their results, and they looked like this. They match. Yes, isn't that great? There are gravitational waves in the universe that are consistent with merging supermassive black holes. After 15 years of listening, we have figured that out, but we're not done. So we've still got our pulsars. We're still looking, still checking out all the supermassive black holes. The sound gonna go on sound? You can do it. Yes. So remember our analogy again. What we've got now is we've got a very basic kind of fuzzy background for gravitational waves. That is awesome. It's kind of like listening to this crowd noise you're listening to now, and you're kind of like, is it a crowd? Here's something. Okay, maybe there was a voice. We're not done. The IPTA is going to keep on going, keep on finding more pulsars, better pulsars, listen longer. And so now you can hear the crowd, you can hear some voices, you can tell that there's some people talking. And the longer we listen, the more we hear about what it's saying. You can hear individual people talking. And eventually, crowd merging black holes will be revealed to us. We will eventually see, hear, observe individual black holes merging. Can't wait to hear what they have to say. It's going to be great. Thank you very much, everybody, for being here.
Take some questions from the audience.
Okay, in the very back.
What is the medium that the waves are going through? I mean, is it the goo of space? You called it the time.
Space-time.
Space.
Yeah.
What is the wave has to travel through something.
Okay, so the question is, what is the medium that the wave travels through? The wave does not need to travel through something. It is a vacuum. So light can travel through a vacuum, so can gravitational waves. They're both types of radiation. So you don't actually need anything for it to travel through. It just travels through space-time. The fabric of the universe, space-time, is what it travels through.
Yeah, if we go back to that really beautiful slide that looked like a wingspan, and it was looking at the mergers that LIGO has seen over 10 years.
Yes.
I know that the vertical axis is solar mass, but I didn't ever get why is that such a beautiful pattern?
Question.
Yeah, so the question was, the asker understood that the vertical axis is mass. Why is it such a beautiful pattern? There is no x-axis here. It's a beautiful pattern because people made it look really cool. It's not actually like, the y-axis is data and informative, but the rest of it is beautiful.
Oh, perfect reason.
Yes. Okay, and that side.
To your analogy of the voices, if you took a microphone and tuned it to a particular frequency, you would be able to isolate down to a much more minute fraction. Do gravity waves exude anything like a frequency in that sense?
Okay, so the question was, if you take a microphone and tune it to a specific frequency, you can pick out specific sounds. And do gravitational waves have this sort of behavior? And the answer is yes. So each orbiting pair of supermassive black holes will have a frequency of gravitational waves that it radiates, and that has to do with how fast the orbit is. So if they're going quicker, it'll have a higher frequency, lower frequency. And so that is definitely something that the pulsar timing array folks are looking for. Right now, they're searching through all the different frequencies. And right now, it's just consistent with a whole bunch of black holes all over overlapping. The longer and longer that we do these observations, specific frequencies will probably stand out and we'll be able to identify individual merging black holes.
So gravitational waves, do some gravitational waves collide and then create like a bend in that wave and then a secondary wave? And would that be even harder to detect? Or would that, how do you differentiate that.
Yeah. So the question was, what happens if gravitational waves collide? Is there weird stuff that moves on that goes on that makes it harder? Kind of, yeah. So, like any wave, whenever you have waves that collide and overlap, they do this thing called interfering. So you have waves that are going together, they like add up and make a bigger wave. But if they're opposite each other, like cancel out and make nothing. And so that happens with light, that happens with water, that happens with sound, that happens with gravitational waves as well. So that is something that we have to keep in mind. But I'm not sure how important it is in our detections. I actually would like to think about that more.
How would they go like that?
If they go like that and they're exactly equal to each other and in phase, they would cancel out, but the odds of that are very low.
Are all supermassive black holes found within a galaxy? Do they exist anywhere else?
That's a great question. So the person asked, are all supermassive black holes found within a galaxy? Do they exist anywhere else? I'm really interested in the answer to that. We don't really know, because if they are somewhere else, it's really hard to figure out that they're there because they're dark. And so how do you know if there's a black hole just lurking in the vacuum of space by itself? You kind of can't know. And so the answer is, I don't know. No one else does either.
One more, just brief one. If the universe is expanding, how can they collide? Why are they not all moving away from each other at whatever speed that is?
Right. So if the universe is expanding, how can things even collide instead of just all move apart? Great question. So the universe is expanding, but if you have clumps of things that are together gravitationally bound, then those things aren't going to expand because the gravity is stronger than the expansion. Like, for example, we are not expanding because of the universe. We might be expanding for other reasons, but not because of that. And that's because the chemical bonds that hold our bodies together are stronger than the expansion of the universe. And the Earth is not expanding because of gravity of the Earth is stronger. And so as long as there's enough stuff close together, and gravity is the thing that controls what's going on. But if you've got like a bunch of stuff here and a bunch of stuff here, and then the universe expands, then these two bunches might not ever hit each other. Okay.
You said that we've been listening for about 10 years.
Mm-hmm.
Did most of these get detected early on when you switched on that detection?
For the LIGO ones.
Is it slowing down now? Is that why you have to get a bigger one?
So the question is, if we've been doing LIGO for 10 years, were most of them all done in the beginning, and they've been slowing down, or not? They've actually been speeding up because there have been some upgrades to the instrument. And so in the first round, there were 6. And then in the second round, there were kind of a few more than that. And then after the next upgrade, there were 100. So they run it a while, and then they upgrade it, and then they run it a while, and then they upgrade it. And so then there's more and more. Just awesome. Yeah.
You gave the analogy of the drops in a puddle and constantly gravitational waves forming. And then you were talking about having a baseline for the pulsars. How do you ever get a baseline if gravitational waves are constantly ebbing and flowing?
Great question. So the question is, if you've got your raindrops in a puddle or your gravitational waves all over the place, how do you ever get a baseline for the pulsars? That is what the pulsar scientists do. The pulsar scientists make models of the pulsars to exquisite extreme detail to understand exactly what is going on with this pulsar so that you understand everything about it, and there's something that's still wonky. That's the gravitational waves. I am not that scientist. I do not do that. I admire those people. Yeah.
What programming language do they use to analyze the pulsars and stuff?
Programming language do they use to analyze the pulsars? I know a bunch of people who use Python, but there could be others as well. Yeah. I don't actually know. Who knows? Anyone else?
Need to be done very fast, so they can be written on GPU.
Oh yeah.
They can be written on C++, a variety of languages to speed up the stuff.
Yeah, GPUs have become very helpful in recent years. Yeah.
So the gravitational waves bending in space-time, does that hit the Earth? Does that have an effect on us? Does it move us? Do we feel that? Can we perceive it?
Can we perceive the effect of gravitational waves on the Earth? Nope. Definitely not. If there was a merging black hole like right next to us, we would. Then we would have bigger problems. Oh.
When LIGO first found merging black holes, I think you had, it was like 8 and 24 solar masses or something along those lines. And there was a resultant loss of mass from that merger, like about 7 solar masses.
Mm-hmm.
And now, so then the expression of that loss appeared to have been through gravitational waves. There were no associated gamma ray bursts or neutrinos, correct?
Correct.
Okay. And so what explanation is there for the conversion of this mass into potentially time-space, where time, space, and mass energy would actually be expressions of the same thing in the same way that in chemistry an allotrope of an element would be a different expression of that element, yet not the element would still be itself, like ozone and oxygen, for example, or the phosphorus or tin or whatever. So would that be like the destruction of like the Higgs boson and then into gravitational waves?
Okay, I'm struggling to repeat this question because it's long. So the speaker said, so when black holes merge, some mass is actually lost, and that energy is converted into the gravitational waves. And so you heard of E equals mc squared, Einstein. So Einstein also predicted how this would happen with black holes. So if black holes were orbiting and there were not gravitational waves, they would orbit forever, never merge. And so the reason that they merge is actually because the orbit loses energy. E equals mc squared, E is energy. And so if you lose energy, that means that energy has to go somewhere because energy is always conserved. And so that is the gravitational waves that are going out. So the gravitational waves carry the energy away. What was mass, the m in E equals mc squared is mass. Mass is converted to energy. So the energy conservation is happening as the orbit gets closer and closer. It's because the gravitational waves sending the energy away. And the amount that is lost in the black hole mass is equal to the amount that goes away in the gravitational waves. Did I answer your question, or did I just explain something that you also explained?
Well, I didn't explain it.
Are we out of time? Sorry, we can talk about it later.
Please come up if you had a question and we didn't get to call on you. And thank you again.
Thank you, everybody. Thanks for coming.